Hey guys, Miss Marisek here, and in this video we're going to talk about an introduction to spontaneous reactions, as well as talk about entropy. Now, one of the big concepts of Unit 9 are calculations to determine whether or not a reaction is spontaneous or non-spontaneous at a given set of conditions. And so what I wanted to take a moment and do first is to define what it means to be a spontaneous reaction. And it says here that a spontaneous process is one that proceeds on its own without any outside assistance, which means it's a process that naturally occurs on its own at whatever conditions were stated without any kind of significant help. Now, most processes are spontaneous only in one direction. And if I wanted to reverse that process, I would end up causing it to become non-spontaneous, and I would have to help it along by applying an external source of energy. It is not something that would naturally occur on its own. Now, to give you an example of what this might look like, you notice here two flasks. The first flask has all of the gas on one side, where we have a valve that is closed in the middle. And what they've done here is they've opened up that flask, and naturally, all on its own, the gas molecules have worked their way to the other side of the container. Now, hopefully we're familiar with the fact that this seems like a naturally occurring process. We know that gases expand to fill their container. So it makes sense that if I open that valve, that we should end up expanding that gas to the other side of the container. So in this forward direction, our process was spontaneous. It naturally occurred all on its own. However, if I wanted to force this in the opposite direction, if I wanted to get all of these gas molecules back onto a singular side, I would need to apply a lot of work, a lot of energy to these molecules to force them all to go back to that one side. And so in this reverse direction, my process is non-spontaneous. Now, this just involved the expansion of gases, but I could apply this same kind of idea to phase changes or to reactions, to any kind of process. There's multiple types of processes that could be spontaneous or non-spontaneous. So to give us an idea of some of these processes that we could look at, we're going to look at three scenarios down here. And for all three of these, they are processes that we're hopefully familiar with. And so we want to think about if they're spontaneous or non-spontaneous at the stated conditions. So looking at our first example here, we notice we have liquid water becoming solid water. So that process is freezing and negative 10 degrees Celsius in 1 atmosphere. So that's standard atmospheric conditions here. However, notice that temperature. I know that water freezes at 0 degrees Celsius, so if I'm at negative 10, this should definitely freeze. So what that means is that in this direction, at these set of conditions, this particular process is spontaneous. I would expect to see water freeze at negative 10 degrees Celsius. However, if I wanted to reverse that process, I would need to apply some extra energy to get a solid to go back to a liquid at these conditions. More than likely, I would need to raise the temperature. So it's not something that would occur at that exact set of conditions on its own. So again, the reverse process is non-spontaneous. Now let's look at the next one. We have liquid water that is decomposing to form hydrogen gas and oxygen gas at standard room conditions. Now, I hope we know that water sitting in a beaker on our lab table would not just spontaneously decompose into hydrogen gas and oxygen gas, that it's going to stay as the liquid water, right? That's what we would naturally expect to happen, is it to remain as the water. So this particular process is not spontaneous. In order to get liquid water to decompose like that, I would have to add in an extreme amount of energy to do that, more than likely in the form of electrical energy. If I run electricity through liquid water, if I expose it to high voltage, I can get it to decompose like that into the gases. It's not something that happens on its own. So now let's look at the last one here. We have NaCl, table salt, sodium chloride as a solid that is splitting up into ions that are aqueous, so dissolved. If I put 1 gram of table salt into an entire liter of water at room conditions. So let's think about this. Would we expect a little bit of table salt put into water to dissolve and split into ions? And hopefully the answer to that is yes, we would expect that to naturally occur at those conditions, right? So again, this being a process I would expect to happen at those conditions, that would mean that this is spontaneous. It naturally occurs on its own at those given set of conditions. Now, if I wanted to reverse this, again, I would need to apply some work, some energy to get that to happen. More than likely, to get the table salt to go back to a solid, I would need to evaporate off the water. So I'd need to heat this up in order to get that to happen. But again, what that means is that the reverse process is non-spontaneous. I have to force it to happen. So here's the issue though. All of those processes are ones that we have some familiarity with. Like we kind of knew for those processes whether or not those should occur. But what happens with processes that we're not familiar with? We have to be able to calculate those processes to determine whether or not they're spontaneous or non-spontaneous at a given set of conditions. And so that's one of the things that we're going to be doing within this unit. Now, before we get any further, I do want to clarify a term. For College Board, for AP Chemistry, instead of using the word spontaneous, they typically instead use the term thermodynamically favorable, because we're going to be looking at some thermodynamic conditions for enthalpy, entropy, temperature, and we're going to determine if it's favorable to occur in a particular direction. Now, I know that seems kind of silly to use that long term, but College Board likes that term better than the term spontaneous. And so you will see them referencing questions being thermodynamically favorable or thermodynamically unfavorable for non-spontaneous. So just keep that in mind, that you're going to see that difference in terms being used. However, I will warn you, if you're taking chemistry in college, your professors are probably going to still use the term spontaneous and non-spontaneous. So don't be surprised to not hear them use thermodynamically favorable. Now, one quick thing I want to note is that when we are determining if something is spontaneous or not spontaneous, we are actually not indicating any kind of information about the speed at which that process could occur. We're just basically saying it's likely to occur in that direction, but it could be occurring quickly or it could be occurring slowly. We have no idea. We would if we studied the kinetics of that reaction, but that's not what we're doing here. We're only determining whether or not that process is likely to happen or not. Now, some of the variables that we're going to use to determine if processes are thermodynamically favorable include enthalpy. So hopefully we are familiar with that from back in Unit 6. We're going to be revisiting a lot of those enthalpy calculations, like where we used bond energy or heats of formation or stoichiometry to determine enthalpy. So there's all kinds of ways we can figure out that delta H. And so we're going to revisit a lot of those. Temperature can also impact whether or not a process is favorable or not. Entropy is the one we're going to be talking about today. And all three of those variables impact something called Gibbs energy, which we're going to refer to in a later video. Now, all of these things help us to determine if a substance is spontaneous, thermodynamically favorable, if it's not a process we are familiar with. So we're going to have to use these variables within calculations. And so we're going to start off today by talking about what exactly is entropy. Now, for some of you, you've heard of entropy before, especially if you've taken AP biology. This is a topic that commonly pops up in that course. However, unfortunately, a lot of you have probably heard of entropy referred to as disorder. And while that's not a bad term, we can do a lot better. So we're going to talk about a better term to use instead of disorder here in just a minute. And the reason why disorder is not a great term is because disorder is in the eye of the beholder. If I was to walk into your room, you might think that your room is very ordered, like you have very neat piles of things here and there where you know exactly where those items are at. But if I walked into your room or your parents walked into your room, they might be like, this is a hot mess express happening in here. This is like totally unordered. So to me, it looks disordered, but to you, it might be ordered. Order is in the eye of the beholder, so we have to be very careful with that term. It's not always easy to distinguish. And I'm going to give you a great example of that. We see two figures down here. both of which have these little black squares organized in particular fashion. And my question to you is, which one would you guess has the greater entropy? Now, if I say to you, which one has the greater disordered, I don't know about you, but both of them look pretty disordered, right? It's kind of hard to tell which one has more disorder. But if I said to you, which of these has more rules to organize the way it is ordered, or which one has less rules, that might be a little easier to distinguish. So I'm going to ask y'all a question. Which of these do you think has more rules to organize its arrangement? I'm going to tell you a secret. It's figure 2. Figure 2 has an extra rule to organize these little black squares that figure 1 does not. Have you figured out what that rule is? Figure 2 had a rule that no two little black squares could have their sides touch. Okay? Figure 1, you could put those little black squares anywhere you wanted. Now think about this statistically for just a moment. Over here in figure 1, I have a various amount of arrangements that I could place those little black squares in, that I would end up with a wide variety of arrangements that I could have. However, on figure 2, once I put that rule in that no two sides can touch, now statistically I end up with less total possible arrangements over here. So more rules means less arrangements. Less possible arrangements actually means less entropy. The more rules I have, the less entropy I have. So, which one has the greater entropy? It's figure 1. Figure 1 had less rules and more possible arrangements to those little black squares. See how tricky that was? So we want to think about this idea of rules about our arrangements. What could limit or expand our number of arrangements that we could have? And in AP Chemistry, instead of calling those arrangements, we actually use the term microstates. So with that said, let's go ahead and flip to the next page. So again, as we said, figure 1 had the greater entropy on the previous page. Why? Again, figure 1's black squares had no restrictions placed on their arrangements. So you had this huge variety of arrangements, this huge variety of microstates that could exist. But figure 2's black squares had the restriction that one square could not share sides. So that means it had more restrictions, and therefore it had less microstates possible. Now, microstates ties directly to entropy. More microstates, more entropy. Less microstates, less entropy. So instead of using that term disorder, I want us to think about entropy in terms of microstates, the arrangements possible. And to give you one more idea about microstates, we have another example here. So this goes back to the gas flask example that we saw on the previous page. If I had 4 molecules, molecule A, B, C, and D, that I was trying to arrange in a 2-sided flask, if I had the rule, the guideline, that only 2 molecules could be on either side of the flask, that would limit me to only 6 arrangements possible, to 6 microstates. But if I loosen those rules, if I provide more opportunities for arrangements, my microstates now goes from 6 up to 16. So we want to think about things we could change in order to get our microstates to increase if we are trying to increase the entropy. So to think about that in terms of chemistry, let's think about things that could help us increase the microstates in chemistry. The first of those is breaking intermolecular forces. IMFs are rules that dictate the arrangements that molecules could have. You have to have the partially positive and the partially negative attracting each other to make the IMF. It's rules for arrangements. So if I can break those IMFs, that could cause our number of microstates to increase. I have more possible arrangements of those molecules. Next thing I could do, which hopefully makes sense, I can just simply increase the number of molecules. If I have more molecules, then we can make more arrangements and more combinations, and so therefore our microstates would increase. The last thing I could do is I could increase the temperature. If I increase the temperature, what that means is if you think about a Maxwell-Boltzmann distribution curve, which we'll revisit here in just a little bit, that would expand the various amounts of energies that exist in that sample. When I have a lower temperature, I have a smaller range of energies. When I have a higher temperature, I expand that range of energies. The bigger range of energies I have, that causes a greater number of arrangements of those energies, greater number of microstates, and so those microstates increase with increasing temperature. Now, all three of these things that we talked about, breaking IMFs, increasing molecules, increasing temperature, all serve the goal of increasing our microstates. And if we increase our microstates, we increase our entropy. So with that said, let's go ahead and look at the next page. So as I mentioned just a moment ago, the larger number of microstates that are possible indicates a higher entropy. So again, don't think about entropy in terms of disorder. Think about it in terms of microstates, in terms of arrangements. So if a particular process has a positive value for a delta S, the change in entropy, that means we have an increased amount of entropy, meaning that we had an increased number of microstates, which means there were less restrictions on the arrangements, less rules, less IMFs, greater number of molecules, all those things that would decrease that amount of restrictions on arrangement. Now, if I had a negative delta S, that means I have a decreased entropy. That means I had a decreased number of microstates, which were more restrictions on arrangement. So think about the things that could limit your arrangements. Things like increasing the IMFs or decreasing the number of molecules. If I limit the number of arrangements, I'm going to see a decrease in that entropy. So we have down here a couple of scenarios that are pictured, and what they want us to do on each of these is to indicate what kind of change is occurring and also indicate the direction of entropy increase for each of these processes. So on this first process that's pictured here, we have a reaction where I'm going from 5 molecules of a particular gas to 10 molecules of a particular gas. Now, this is represented as a picture, but you could also represent this same thing as a balanced reaction. Now, the balanced reaction here would be 1 N2O4 going back and forth between 2 NO2. So again, we see that 5 to 10 or the 1 to 2 ratio remained in those two different ways of illustrating our process here. So in going from 5 molecules to 10 molecules, we're increasing our number of molecules, meaning we're increasing our number of arrangements that we could potentially have, the way we could organize all of those particular molecules, which means we've increased the number of microstates, which means we've increased our entropy. So we're going from a less entropy situation to a more entropy situation, meaning this reaction, this process would give us a positive delta S value. All right, let's look at our next one. Now, this next one is interesting because there's actually 2 things that change in this picture. You notice they're doing a gas law experiment where they have a particular gas at a volume and they're heating it up. And once it got to the higher temperature, we noticed that our gas has expanded. So not only have we changed the volume with this situation, but we've also changed the temperature with this situation. And actually, both of those things on their own could change the entropy. So when both of those things change, we're definitely going to see a change in the entropy. So to kind of talk us through here, if I increased the volume, having a greater amount of volume means that I could have more arrangements. There's more kind of places that I could put those molecules. However, even just the temperature would cause a change. Remember, when I increase the temperature, I increase the range of energy values that I get. And to see that again on a Maxwell-Boltzmann curve, remember at a low temperature, our curve is more condensed. At a higher temperature, our curve gets more expanded. So we expand that range of speeds that we see here. And so what that means is that if I see a wider range of speeds, that there's more arrangements I could have of those speed values. And so both of those processes would increase the number of microstates, which would end up increasing the entropy. So from the perspective of both volume and temperature, I'm going from a less entropy situation to a more entropy situation. And so in this direction, I would see a positive delta S change. All right, we've got one more situation down here. And on this one, we notice some phase changes occurring. We're going from a solid to a liquid to a gas. So let's think about this for a second. If I'm going from a solid to a liquid to a gas, that means I am changing my IMFs. I'm breaking those IMFs. Over here is a solid. Those IMFs are high, meaning there's less freedom to move those molecules around. Their position is pretty much stagnant where it's at. However, as I go from a liquid then to a gas, I'm breaking those IMFs. I'm decreasing those IMFs. And so I'm increasing the freedom that those molecules have to move around. And so if I decrease the IMFs or increase the freedom to move, both of those things would end up increasing the arrangements of those molecules. There's a lot more ways to arrange the molecules over here than they were as a solid. So that would increase my microstates and that would increase our entropy. So again, I'm going from a less entropy situation to a more entropy situation. So in this direction, we should see a positive delta S change occur. Now, I put a little graph over here because I want to show you something. This graph shows the temperature increase and the entropy change that's occurring. So notice this temperature increases as a solid. We do see an entropy increase, but notice what happens when I melt as I transition from a solid to a liquid. We get a huge bump in entropy at that point. So again, we increase entropy as we increase temperature, but then we get here to where we boil, and again, we see a huge jump in that entropy. So while entropy is increasing all along here, I see more increase in entropy at a phase change than I do if I'm just simply increasing temperature. So that's why I wanted to show you this, is that IMF changes have a much bigger role in changing entropy than just simply increasing the temperature. And that graph does a great job of showing that. All right, let's go ahead and flip to the next page. All right. So on this particular example, we have a dissolving process that's occurring. And what they want us to do is for each of the steps in the dissolving process, they want us to indicate what kind of change in entropy are we seeing, but then they also want us to indicate the entropy change for the whole entire process. And so we need to look at each of our steps individually first. So step number 1 here, we have our solvent breaking apart. So what that means is that here I'm decreasing the IMFs, I'm breaking those apart. So that would help me to have more arrangements possible here, so more microstates. And so therefore my entropy in this step would increase, and I should see a positive delta S value for step number 1. Now step number 2 is the solute here breaking apart. I have a solid actually here that's going to get dissolved. And so again, in breaking up those particles, I'm breaking up the intermolecular forces that are existing here, meaning I'm going to have more arrangements possible and more microstates. And so therefore that would increase my entropy and I would have a positive delta S for that step as well. So now that we've broken all of our IMFs, we're going to put those two substances together and reform my new combination intermolecular force. And so in reforming a new IMF, that would actually decrease my microstates because I'm going to limit the arrangements once those new interactions form. So in this step, I would actually slightly decrease my entropy and I would have a negative delta S for this particular step. However, here's the deal. Overall, even though these steps individually had a delta S value to them, we can still have an overall delta S that takes place. Now, because I'm combining together substances, that provides a lot more opportunity for arrangements and combinations that could take place than either of these had individually. So since I have all of these particles and all of these combinations coming together, those arrangements skyrocketing gives us an increased number of microstates overall. So overall, I'm going to see an increase in entropy and a positive delta S value. By the way, this is true for any time I'm doing some sort of dissolving process where I'm combining things together in a solution. Because I'm taking all of these individual particles and mixing them together, that provides way more opportunities for arrangements. So anytime I'm doing a solution formation, a dissolving process, overall, I'm going to see a positive delta S value, even though my steps individually could be positive or negative. All right, here's what I want you to do. On the next example, it says for each of the following processes, you want to predict if the process represents an increase or decrease in entropy, or if it stays relatively the same, hint, hint, and predict the sign of your delta S. So what I want you to do is to take a moment, pause the video, and go try out this example. All right, did you pause it? Did you try it out? I'm going to go ahead and throw my answers up here, and you can see how you compare. Now, I may have put a little bit more information here on these than you did because I went ahead and kind of showed exactly what changes are taking place besides the entropy and the delta S value. So on here, on this first example, we have a solid that is dissolving into aqueous ions. And I noticed two things happen here. First off, I'm going from a solid to aqueous here. So that means I'm going to have increased freedom of motion in those aqueous particles. But also I have an increase in the number of overall particles. I'm going from 1 particle on the reactant side to 4 particles on the product side. Also, as a hint, this is showing a dissolving process. And as we just said with the dissolving process, I should see an increased number of microstates, an increased number of arrangements overall. So here I'm going to see an increase in entropy, and my delta S value should be positive for this process. For the next one, I have bromine as a liquid going to bromine as a gas. So in that vaporization process, I am getting a decrease in the intermolecular forces. They are getting weakened. And so I'm going to see more freedom of motion occur. So as I break those IMFs, that would increase my number of arrangements, my microstates. I should see an increase in entropy, and we should have a positive delta S value. Now this one, if I first check my states, I notice that I'm going from gases to a liquid. So I am getting here an increase in intermolecular forces. But also I notice that I'm going from 3 reactant particles to only 1 product molecule. So I also have a decrease in the number of particles that are taking place. So all of these changes together help to reduce the number of microstates, to reduce the amount of arrangements that I see. So this should have a decrease in entropy and a negative delta S value for this process. Now on this last one down here, if I checked my states, I noticed it was a gas all the way through for both reactants and products. So I had the same IMFs, but I also noticed that I had 3 gaseous molecules on the reactant side and 3 gaseous molecules on the product side. So 3 molecules and 3 molecules means that the number of particles stayed the same from side to side, which means here on this one, we actually had a relative constant entropy. And I know some of you are thinking, man, Miss Marisic, this one was a trick. I know it was kind of a trick, but here's why I put this one on here. I want us to see that not always can we truly predict the actual sign of our delta S just by simply looking at a reaction. This one, it's kind of hard to tell. I mean, we think it's relatively constant, but it could be slightly positive or slightly negative. And the only way to know for sure is to do some sort of calculation to solve my delta S value. Also, if I was presented with this situation where maybe the IMFs contradicted what the particles were doing. So like, for example here, what if the IMFs had increased, but your number of particles had also increased? It would have been really hard to tell then at that point if your microstates had increased or decreased. So the issue is this is not always easy to tell what's happening with our entropy. So sometimes we are going to have to do a calculation to help us really know what's going on with the change in entropy for our process. Sometimes we can predict it, but sometimes we're going to have to do that calculation. All right, I hope we're feeling pretty good about identifying increases and decreases in entropy. If you have any questions or need any help, please feel free to email me. Bye, guys.